Hi, I'm William, and today I'm going to talk about what I call the quantum supremacy Tsirelson inequality. So arguably the single most important and famous inequality in all of quantum information is the so-called Bell inequality. And the reason why the Bell inequality is so important is that it makes an experimental prediction about classical mechanics that can be refuted by quantum mechanics. In particular, what the Bell inequality says is that there's this game you can play called the CHSH game, which involves a referee and two non-communicating players, Alice and Bob, such that the probability they win this game using any strategy that can be explained by classical mechanics, essentially, um, the probability they win in that case is at most 3/4 or 75%. And hence, if you can show an experiment in which two players play this game without communicating, and they win with probability greater than 75%, then somehow you've revealed something inherent about the non-classical nature of the world. And indeed, we know actually that assuming the two players share entanglement, let's say even just a single EPR pair, then they actually can do slightly better than 75%. In fact, they can win with probability cosine squared of pi over 8, it turns out, which is about 85%. So just slightly better. But this also raises the very natural question of, well, suppose they had like unbounded quantum resources, then what's the best that they could do quantumly? And it turns out, well, so this brings us to arguably the second most important inequality in all of quantum information, which is the Tsirelson inequality. And the Tsirelson inequality says that actually, assuming quantum mechanics, this cosine squared pi over 8 is also optimal, which is kind of remarkable if you think about it, right? You could imagine getting all the way up to 1 by some arbitrary correlations or something, but even in this case, it turns out quantum mechanics is somehow limited. And besides just being a very natural question to study, right, we also now know in hindsight that the studying the Tsirelson inequality was sort of the basis for the modern study of non-local correlations and non-local games, which very recently has culminated in some fantastic results, including MIP star equals RE and the refutation of the quantum embedding problem in operator algebras. So this is certainly an important question to study. What I'm going to argue next is that something very similar is happening in the world of quantum supremacy. So recently, as in just a little bit over a year ago, a team based at Google announced the first experimental demonstration of quantum computational supremacy. And they did it for a task called random circuit sampling. And the way this works is Google would choose a random quantum circuit Z. So it's an n-qubit circuit of random 1 and 2 qubit gates, which I've stylized in this figure. And the task they attempt to solve is what they call the linear cross-entropy heavy output generation task, where your goal is to output a string Z on n bits such that this quantity is as large as possible. And if you're wondering what this quantity is, this is just the probability of measuring Z under like the true output distribution of C. So if you were to simulate C on like a noiseless quantum device, this is the probability with which you would see Z. Now, also just a little bit over a year ago, Aronson and Gunn proved a computational analog of the Bell inequality for this XHOG task, where they showed that for any under a plausible complexity theoretic conjecture, no polynomial time classical algorithm can do substantially better than random guessing for this XOG task, right? Note that if you just guess Z uniformly at random, you'll achieve like you'll achieve a linear cross entropy score of like 1 over 2 to the n, just because there are 2 to the n total output strings. And Aronson and Gunn show that this is probably optimal. This is probably the optimal guessing strategy of computationally bounded classical algorithms. And hence, when Google announced a quantum computer that achieved roughly 1.002 over 2 to the n, where n is like 53 qubits, this is basically enough for them to claim the first real demonstration of quantum supremacy. And just like on the previous slide, it's also extremely natural to ask, well, what's the best that one could do for this problem using, say, let's say we had like a noiseless, perfect quantum computer, fault tolerant, but we're constrained by polynomial time. What's the best you can do? And this is what I call, the quantum supremacy analog of the Tsirelson inequality, right? And just like on the previous slide, there is like a better quantum algorithm. Namely, if you actually just run the circuit C, and just as long as the circuit C like looks sufficiently random, then it turns out that like on an ideal quantum device, you would achieve a linear cross-entropy score of roughly 2 over 2 to the n. So better than this 1 over 2 to the n. And also sort of comparable to on the previous slide, there is like a trivial information theoretic upper bound. So it turns out that, again, if the circuit C is like sufficiently random, and if you manage to somehow always find like the largest amplitude of an output string Z, then if you always output that, then you would achieve roughly order n over 2 to the n. But, again, this is sort of not really satisfying, because what we're interested in is what's the best that a computationally efficient quantum algorithm could do for this linear cross-entropy benchmark. And that is the problem we study in this work. And in this work, we study this problem in basically the simplest non-trivial model in which this question is interesting. And that is to say, we study it in the query or black box model, meaning we treat the circuit C as a black box. So the quantum algorithm only gets to make queries to C. And we'll also treat C as like a perfect Haar-random n-qubit unitary matrix. And our main result shows that for this task, if you want to do substantially better on this linear cross-entropy benchmark than the trivial quantum algorithm, then you actually need to make an exponential number of queries to C. Roughly like 2 to the n over 4, where n is the number of qubits. We also have some other results in this paper. So in some cases, we can actually replace this Haar-random oracle by other oracles. And we also show a upper bound. So we can show a lower bound of like 2 to the n over 4 for this task. But we can also show that you can also do slightly better than 2 over 2 to the n using just 2 to the n over 3 quantum queries. And this is based on an algorithm that uses the quantum collision finding algorithm. So there are a few reasons to care about this. Arguably the most obvious one is that, well, it's a real world problem. If you care about algorithmic lower bounds, you should certainly care about lower bounds for the only quantum algorithm that anyone has ever implemented, right? I mean, indeed, one could even argue that this is, to this date, the first and only algorithmic hardness result for a quantum algorithm that has actually been implemented. Another reason, though, is that it turns out this problem is sort of interesting in its own right, even in this very restricted setting of quantum query complexity. And this turns out to be because this problem really differs a lot from the normal problems we tend to study in quantum query complexity. Most query complexity problems involve Boolean oracles. So you query like an n-bit string and you get a 0 or 1 answer. But here, the oracle is sort of inherently this random quantum unitary, which is very different. Additionally, most query complexity problems we study are decision problems, and this is not, right? The task is to output some n-bit string satisfying a certain average case property, and there's really no way to reduce this to just like a decision problem. And these two things combined actually basically mean that all of the existing tools, all of the existing lower bound techniques for quantum query complexity are not going to work here. So for example, the adversary method, which is very popular because it is known to tightly characterize the quantum query complexity of decision problems, is basically useless here because it's not a decision problem. Um, the polynomial method, in principle, could be used here, but it would be probably a lot more cumbersome than normal because, again, you don't have these Boolean variables, but you have these, completely hard random entries. So both of these kind of suggest that we need some new ideas to be able to tackle a problem like this. And that's what I'm going to talk about next. So I'm just going to say a little bit about what I thought were some of the interesting ideas that went into this work. And I'll start with the one I thought was sort of the most likely to perhaps be applicable elsewhere. And this is something involving so-called state preparation oracles. So imagine I have some n-qubit state psi, and I want to give my quantum algorithm access to psi. So how can I do that? Well, the simplest thing you could do is just give the algorithm copies of psi. But really, what you'd like to be able to do is say, the algorithm should be able to make as many copies of psi as it wants. What I want to do is give you a unitary that allows you to produce copies of psi. And in the literature, the most common way we tend to give algorithms access to such unitary is by what I like to call this canonical state preparation oracle. And the way this works is we fix some canonical orthogonal state, which I'll denote by bot, and we'll consider the unitary U that acts as follows. So it swaps bot and psi. So if you feed in the state bot, which you can think of this as being like the all zeros input or something. If you feed in the all zeros input, you get back a copy of psi. If you feed in psi, you get back the all zeros input, and otherwise this unitary just acts completely trivially. The reason I call this the canonical oracle is that besides being like arguably the simplest way to produce copies of psi, it also turns out that such an oracle essentially follows in like a black box way from pretty much any other oracle that lets you, any other unitary oracle that lets you produce copies of psi. But okay, but for the purposes of our work, it's actually very natural to consider what looks like a priori and completely different model of state preparation. So consider I give you a unitary where I promise you that the first column of this unitary contains psi, which is just another fancy way of saying that on the all zeros input, this unitary produces a copy of psi. But everywhere else, this unitary is going to be essentially completely random, even like hard random. So there's no guarantees on what it's going to be elsewhere. And somehow this feels very different, right? Because this is a unique canonical oracle, whereas this is like an ensemble of oracles even. So what can we say about their relative power? Well, it turns out one of the key lemmas in this work shows that actually in the query complexity world, these two resources are essentially equivalent in the sense that either one can approximately simulate the other to like inverse exponential precision in the number of qubits of psi using a constant number of queries to the other. I guess I suppose like the left implication was already known because like I said, this is sort of the canonical oracle, but the right implication is what's new. And I could imagine, this could be used elsewhere where state preparation oracles show up. So in certain like cryptographic protocols, for example, this might be useful. But for our purposes, it is very useful because it allows us to replace this random oracle by this conceptually much simpler object, this canonical oracle. And indeed, for this canonical oracle, we actually have some nice tools for proving lower bounds. In particular, there's this theorem by Ambayanis, Rosmanius, and Unruh in 2014, which shows that if I have a quantum algorithm that makes queries to this canonical state preparation oracle, I can actually simulate this algorithm approximately by a different algorithm that makes no queries at all and instead starts with a resource state. And what this free source state consists of is a bunch of copies of psi in superposition with something else. And the number of copies we need is like roughly the square of the number of queries the algorithm makes. And this is very nice. And actually, for our problem, it even allows us to simplify it even further. So whereas in this original theorem, you need copies of psi in superposition with something else. Actually, it turns out for this problem, because of the symmetries of the problem involving these output amplitudes of this linear cross entropy score, you can actually just reduce it to algorithms that just start with a bunch of copies of psi. So you make t queries, you can just consider algorithms that instead start with like t squared copies of psi. And there, it's actually relatively easy to get a lower bound using, again, the symmetries of the problem. I guess the intuition here turns out to be that if you only have copies of psi, and you want to measure a string z such that the amplitude on z is large, basically your best strategy is to just measure a bunch of copies of psi and output whichever thing appears most often. And intuitively speaking, you're not going to do much better with a bunch of copies of psi than with one copy of psi, unless you are able to start seeing collisions. So you measure the same string z multiple times. But then this sort of turns into like a birthday paradox problem. If there's like 2 to the n possible outputs, you need like 2 to the n over 2 measurements to start seeing collisions. And that's actually basically where this lower bound comes from, right? So you need at least like 2 to the n over 2 copies of psi, and with 2 to the n over 2 copies of psi, you could simulate like 2 to the n over 4 queries to this state preparation oracle. So that's like the very high level overview of the important ideas that went into this and how they contribute to the final lower bound. So I'm just going to conclude with some of my favorite open problems relating to this. Perhaps the most obvious one left open is to tighten the bounds, right? So right now there's a gap between our lower bound and our upper bound. I actually conjecture that this 2 to the n over 3 is probably tight, and that this 2 to the n over 4 can be improved. And I even have some ideas for how you might be able to improve this, which I discuss in the paper. But for the time being, I have no idea. Another obvious question, I guess, is to give some stronger evidence that this problem is actually hard in the real world. So for instance, for the classical analog of this problem, what I called the classical computational Bell inequality proved by Aronson and Gunn, they gave a reduction to a problem which involves estimating the output probabilities of random quantum circuits. But it sort of looks like such a reduction is just not going to work here because the assumption they start with is simply false for quantum computers. So it seems like probably some new ideas would be needed to give other evidence of hardness in the real world, where you don't just have query access to the circuit, but where you actually have an explicit description of it. But even like simpler problems, I feel like are we don't really know how to answer. And actually, one thing I think might be interesting to explore is to what extent do these random quantum circuits exhibit computational pseudo-randomness properties, right? So sort of implicit in his work is some assumption that if you replace this distribution of random polynomial-sized quantum circuits by the Haar measure, then computationally, your algorithm is still going to do basically about the same on this linear cross-entropy score. And somehow this is a sort of like pseudo-randomness assumption, even in this restricted query complexity model. And I think it would be nice to better understand like to what extent this assumption is well-founded. So we know that like in certain regimes, random quantum circuits sort of information theoretically approximate the Haar measure, but I actually conjecture that there should be a stronger pseudo-randomness property that holds against even like exponentially powerful quantum algorithms. And it would be nice to give some evidence for this, or just to better understand these sorts of questions. So that about concludes the talk. So that's everything I wanted to say. If you have any questions, you are more than welcome to email me, but otherwise I will see you at the live version of this talk in ITCS.